Welcome back to Essential Perturbation Theory and Asymptotic Analysis. Any questions before I get started? From the audience or online? Okay, if not, then we're gonna start a new chapter today. And the method we're going to talk about is called the WKB method. This method was originally developed as a method for approximating solutions to the time-independent Schrodinger equation, but has been more broadly and widely used since then. It was developed in the 20s, according to one legend, and it goes by the name WKB after the inventors, Wenzel, Kramer, and Brion. But there was a guy named Jeffries who actually was earlier in 1924 who developed something more or less the same. This was around the time that quantum mechanics was becoming a thing. And when it was starting to become a thing, well, especially after the Schrodinger equation was invented, solutions to this linear equation, which could sometimes be rather difficult, were needed. This is an approximation method for solutions to the time-independent Schrodinger equation. And the reason why you can use time independence is because of the principle of superposition. So even for this linear equation, it can be difficult to solve these problems exactly analytically. Now, the nice thing about the Schrodinger equation is there's a small parameter in that, namely the Planck's constant. So with a small parameter, you can do perturbation sort of methods. Now, these seem to be singularly perturbed problems, but not singularly perturbed in the exact same way that the equations we saw in chapter 5 are singularly perturbed. In chapter 5, we had a small parameter such that if we set that parameter equal to 0, we got an outer solution or an outer equation, which had some sort of reasonable structure. Here we're going to see, and of course, that kind of gave rise to, in our typical boundary value problem where we had a boundary layer at, or boundary layer problem where we had a boundary layer at the origin, say, we'd get something which looked a bit like this. And if we set the epsilon parameter to be 0, we got more or less the outer structure of the problem converging to something. In some sense, you could say that as epsilon gets smaller and smaller, the solutions converge to more or less something which is basically the outer solution plus a point and a transition where you have to transition from the red curve into that point. But the problems we'll see here are not singularly perturbed in exactly the same way, though the structure looks quite the same. The other thing I want to mention about the WKB method is that it is a global method rather than a kind of piecewise method that you would that I would describe the matched asymptotic method as. So in matched asymptotics, we tried to construct a solution from the perspective of computing it in the inner solution region and the outer solution region, and then trying to sew them together in an overlapping region. But the WKB method is going to be different in that we'll be able to get an approximation globally from the start. It also handles two different types of phenomena, as we'll see. On the one hand, we're going to deal with what are called dispersive types of equations. And by that, we mean solutions which are oscillatory, and diffusive type of equations, whereby we mean that the solutions tend to have asymptotic decay or growth type of behaviors, usually asymptotic decay. Our treatment in this section is going to fairly closely follow Bender and Orszag. I don't understand this material as well as I understand matched asymptotics, so this is newish for me. And so I don't have the best designed lectures for this, but as I get to know it and as we get to sort of simultaneously know it pretty well, then I think the lectures will sort of evolve to something a bit nicer. So these won't be as polished, I think, and won't be as theoretical as the lessons we've done previously. This will be more of fly by the seat of our pants and hand waving.
I have a quick
Okay.
question. So this is a new class of method. Does it correspond to like a new class of problems? Or can we use the old method to handle the new Schrodinger equation?
So both. It works for old problems and new. So we are adding a bunch of new problems that match asymptotic simply can't handle. However, it doesn't cover all of the problem types that we've discussed previously. For example, it does not work for nonlinear boundary layer problems. So the last 2 or 3 problems that we discussed in the chapter 5, it won't solve those.
And also there's a typo in the first. The cover.
This one here or this one?
Previous. Chapters X.
Oh, yeah. Thanks for pointing that out. So I forgot to change that and that. So these notes will be extensively updated. If you look at them, as those of you have these in real time will do, I'm sure, you'll notice that the last 5 or 6 slides are kind of crappy and not well designed. I was just kind of throwing them in there in the 10 minutes leading up to class. I don't think we'll get that far, so I think I'll be safe. So these are not quite as polished as I want yet, but they're getting there. Okay, so let's talk about the WKB expansion for the Schrodinger equation. First of all, I want to tell you what is a Schrodinger equation. This is not the Schrodinger equation. This is a Schrodinger-like equation. It's it kind of has the structure of an eigen function problem, which we'll discuss momentarily when we start talking about Sturm-Liouville problems. But for now, we think about epsilon as again being a small parameter. Q is a function which depends only on x, and y is the function that we want to solve for. Q is a known function. So we're going to call this the Schrodinger equation because it has a structure which is very similar to the standard Schrodinger equation after we do non-dimensionalization. So the regular Schrodinger equation has a mass term in it. It has the Planck's constant in there. And so we've non-dimensionalized all those away. I thought about adding a section where I talk about a little brief introduction to quantum mechanics and the Schrodinger equation because it's quite fascinating and interesting. We might still do that. It's not in the lecture notes as of yet. Now, the sign of Q turns out to be rather important. So the way you think about this is as follows. Q can model the difference between the potential energy and the current energy level of a particle. In fact, it's something like, don't quote me on this, but Q is something like the square root of Vx minus E. Something like this. Or actually, maybe it's without the square root. So I forget exactly. But now, so the way it works is if let's see, maybe it's the other way around.
I think it's E minus.
I'm going to try E minus V. Is that it? Oh, okay. It doesn't matter. So if the energy level, let's just imagine this is correct because it's almost right. So if the energy level is higher than the potential, then Q is positive. So that's kind of like saying that your particle is escaping from that potential. However, if E is less than in magnitude this potential energy, then Q is negative. And one sign gives rise to dissipative phenomenon, and the other sign gives rise to oscillatory phenomenon. So it should be something like this. So if that's a potential, you get oscillation in here, and then a decay outside, where you have this transition between V being or E being greater than V or less than V. You have a change in the behavior of the solution. And as I said, if you're interested, you can vote by email or by voice. If you want to see a little bit of quantum mechanics, then we can add a section in that and go through it. But suffice it to say, whenever this changes sign, this changes behavior from oscillatory to dissipative behavior, to decay behavior. Now, the WKB method is designed just for this type of scenario where we have a potential given and an energy level given, and therefore a sign of Q known to us immediately. So we're going to want to develop this WKB approximation, but the way we have to do it is we have to break it into steps. For example, we have to start with the assumption that we're in the negative regime first, and then positive regime, and then negative regime, and do those separately, and then do a matching where there's a transition. So the transition happen at what are called turning points. And so we'll review what happens at those turning points. It turns out that's where all the really hard work comes in. So for now, we're going to start by assuming that Q has a definite sign on an interval or domain of interest. And we'll develop the theory according to that, whether or not Q is positive or negative. Now, the solutions, so I'm going to avoid a description of why the solutions have this form. You'll kind of see that once we do the simpler problems, because when we do a simpler problem, then the solutions are always of this form. For example, if I solve a problem of this form, minus epsilon squared y double prime, so minus q y, let's say Q0, where Q0 is some number. So it can be positive or negative. Then, of course, the solutions to this are simple exponentials. And the sign of Q plays an important role as to whether or not the exponential is decaying or exponentially growing, or it might be oscillatory, so complex exponential. So in that case, so what would the solution be if we had something like this? Well, we do our usual technique, right? So we plug in a solution ansatz of the form y equals E R X, right? And so we say, well, in this case, y double prime, let's do y prime first. Y prime is equal to R E R X, and y double prime is R squared ERX. All right, so we plug that into the equation. What does that give us? We have minus epsilon squared R squared times exponential, but the exponential gets canceled, minus Q naught. So that has to be equal to 0. So we solve for R. R squared is equal to, so in this case, we get minus sign, right? Minus Q naught over epsilon squared. Take the square root. So R squared. And now from this point, we can't really do anything unless we know what is the sign of Q. So R is equal to minus square root. Actually, we'll do it as might as well just say plus or minus, right? Minus, oh, I'm off the page. Right now, at this point, I need to know what is the sign of Q. So in any case, you'll see what happens in this case where I have a simple constant here, no matter whether it's positive or negative, I see that the solutions are exponential type. I also am going to find that I get something like a constant, and I guess that constant is like square root of Q naught plus or minus with plus or minus I, right? Divided by epsilon. So this is the right form of the solution. So the idea of the WKB method is to say, well, okay, in general, we can't assume that this is a constant, but maybe over a certain distance, we can think about this as being rather slowly varying in such a way that this ansatz holds true, or is at least valid in some stretch. The idea is as epsilon gets smaller and smaller, this will become or should become a better and better approximation. Let's see if that pans out. So here's the idea. We're assuming that y is exponential in this function s over delta. And we're also going to assume that s has an expansion in integral powers of delta, a usual or standard asymptotic series expansion, which is valid as epsilon goes to 0. So that's the limit in which we're looking at this. You may also see this if you do look up WKB. Sometimes they'll put the parameter here and say the parameter is getting large, but that's the same as if the parameter is here and getting small. So this is the basic solution ansatz or assumptions for WKB, the setup. We're assuming that S is a power series or an asymptotic power series in terms of integral powers of delta, and we've got to determine these terms Sk, k equals 0 to infinity. The exponential dependence is built right into the solution, and that means, well, that basically means this works for things where that's valid, more or less, which means mostly linear equations, and mostly, or for the most part, it's not going to work at all for nonlinear equations where we don't expect to have such simple solution descriptions. As usual, we're going to assume that if I take the derivative of y, then that can be accomplished by doing a term-by-term differentiation of my asymptotic expansion. Now, this doesn't look like a natural asymptotic expansion because it's exponential of an expansion, okay? We're going to assume, however, that if I were to think about this series as being, or this thing as being term-by-term differentiable, then I could do it in that way. So the derivative of y is just the derivative of my expansion. Now the expansion part comes because this guy here is really a power series, and I'm going to assume that that can be done term by term. And similarly with the second derivative of y, we're going to assume that that can just be tacked on as a derivative of this, and it works out so that I'm basically taking derivatives of the infinite series here and here. Now what we do is what we usually like to do, substitute this into the differential equation. And the first thing we need to do is determine delta, because the only thing we're assuming at this moment is that delta is a function of epsilon that's going to 0 as epsilon goes to 0. So we need to determine the scale of delta, and we'll do that via a dominant balance. If we substitute our solution ansatz into the equation, then we get this new asymptotic equation, which should be valid for epsilon going to 0. I'm not going to replace S with expanded values because we don't need to do that in order to do the dominant balance. Now, if we try to do dominant balance by the standard method, we fail. But the standard method, let's review what that usually involves. The standard method says we should keep this term, right, and balance. And so or I should say this. The standard method involves taking the coefficient in front of the highest order derivative term and using that to balance against the first order derivative term or the 0th order derivative term. But one of the ones that has to survive is this guy in the dominant balance. It turns out that that's not going to work in this case, and it doesn't work for a perfect reason. And the perfect reason is because that these problems are not singular perturbations in the same way that boundary value problems or boundary layer problems were in the previous chapter. Notice that I've already canceled out the exponential term. So there's an exponential term of this form that appears in every term. I'm going to assume that that's not equal to 0 and just cancel it, use standard cancellation. Okay, so this is what I have to balance. Okay, well, if we're to do the balance, then by the standard means, we're want to keep or balance the coefficient in front of the second derivative term with one of the two other lower order derivative terms. So if we try this, we fail, turns out, because we cannot ever obtain a dominant balance if we use this approach. So let's suppose we have only two choices, really. This term balances with either this term or this term, right? If we demand on keeping that, then here's what happens. If we balance the coefficient of the first term with that of the first derivative term, then what we get is delta has to be equal to 1. So let's just do that. If that's the case, that is this term and this term. So we would get epsilon squared over delta squared is equal to epsilon squared over delta. So just solving immediately, you see delta has to be 1. Well, you see that this is an epsilon squared term then. This is epsilon squared, but this is order 1. So that can't dominate an order 1 term. Now, why are we able to assume that Q is order 1? Well, what we're going to assume about Q is that it's never 0 to start with. Remember we said that that's something funky. That's whenever Q is equal to 0, it's at these points called turning points, and they require a lot of extra analysis. So to start with, all that we're going to assume is, I think I might have actually, no, here. I forgot to mention this point, but it is here. We're going to start by assuming that Q is never 0. It could be positive or negative, doesn't matter for us, but it can never be 0. It also turns out we need to assume a little bit more. We need to assume that it can't degenerate to 0 on the domain. Well, this can only happen if you're on an infinite domain. It can degenerate down to 0.
Can we just say that this particular delta of choice doesn't go to 0 as required for, like,
we still are going to need delta to go to 0 as epsilon goes to 0.
Yeah, so that's why this choice is not happening.
No, it's just that so if you use the standard format to do your analysis for these equations, they're not the same as regular singularly perturbed problems, and you get nothing more or less. You get nothing useful. So this is a kind of new thing, okay? So that's the only way I can explain it so far. And I think, to be fair, there's better ways to explain it. It's just my understanding of it isn't quite complete. And that'll improve as I keep typing these notes up and working through these ideas. So I don't know what is the best explanation for why this works. So I'm going to do a proof by approximation. I'm going to show you how good it works, and then we'll come at it that direction. But I'm not doing a good job of motivating, well, why this structure. I do understand that, but suffice it to say, this is going to fail for us. Our standard balancing technique. You can see why balancing this term, the coefficient of this term and this term fails. because this would be order 1, order epsilon squared and order epsilon squared. Epsilon squared can't dominate order 1. Now, so let's try balancing the coefficient of this highest order term with that of the Q term, which is, of course, just order 1. So in that case, delta has to be equal to epsilon squared. So the coefficients in front of the highest order derivative term in Q then are going to be order 1. And that's a problem because the term for the order 1 equation, order 1 term, sorry, the first order derivative term is order epsilon to minus 2 power, which can't be dominated by order 1. This blows up as epsilon goes small. So neither of these two dominant balance cases work, and that's that's one of the designs of the WKB method. It's not meant to work out. So what does work out for this case is not to keep the highest order derivative term in the same way you do in the inner solution region for the boundary layer, the standard boundary layer problems, but to balance the coefficients in front of the Q term and the first order derivative term. Okay, this is contrary to what we usually do for dominant balance, but this is the only dominant balance that works. But this was the dominant balance that was designed to work. Okay, this is a dominant balance that was designed to work. If we do that balance, then we get epsilon squared over delta squared is equal to 1. So here's that term, and it's equal to the order 1 term. So this implies that delta is equal to epsilon. This was what was intended. In this case, the terms of the coefficients of the term Q and dx, the first order derivative are order 1. And now it's okay because what's left over for the highest order derivative term is order epsilon. So 1 definitely dominates order epsilon as epsilon goes to 0. Now, again, I have to point out that in claiming that Q of x is order 1, we've explicitly used the fact that Q is a continuous function and not equal to 0. But actually, you have to do a little bit more because if it's an infinite domain or even an open domain, then Q can become very, very close to being equal to 0. It can decay. So what we need is to be a little bit away from a 0 term. Or away from 0. So what we really need to assume to get an order 1 term there is to assume that Q of x is greater than Q naught for some constant Q naught, or that Q of x is less than Q naught, where Q naught is strictly less than 0. So it's bounded away from 0. It's well bounded away from 0 in either case. So this is what we need in order to assume that the term in front of the Q, or that this whole term is really order 1. So that's just a caveat. So let's go ahead and develop the case where Q is positive. So what I really mean here is that it's well bounded away from 0 on the entire domain. It's bounded, it's positive, it's bounded away from 0 by this lower bound Q naught, which is strictly positive. This is going to turn out to represent the dissipative case. So if you like the picture of the harmonic oscillator, this is that case. So we're in this solution regime and out here, not in this solution regime. So for example, here we might be saying, okay, we're on omega, where omega is 1 to infinity. Okay, so let's now plug in our power series expansion for S. So the power series expansion for S, remember what that is. Right? And we're assuming that we can take term-by-term derivatives of this, of at least first and second order. So we're going to plug that in. And so what happens is the usual sort of thing. We match powers of epsilon on both sides of the equation, and we generate a recursive system of ODEs. So for the lowest order case, notice that it does not involve a second derivative. It involves a first derivative. And again, this is by design. This is by design. This is called the iconal equation, and we'll cover the solution of this momentarily. Doesn't have a second derivative term. The order epsilon term is the first to have a second derivative term in it. It's a linear equation. And of course, but notice that when we solve the order epsilon equation, we're actually after this guy. Okay, so it's actually a simple solution. Right, so once we determine S0 from the order 1 equation, we plug that into the order epsilon equation, and now we're trying to determine we plug it in here and here, and we're trying to determine S1. So actually, this is just a purely algebraic equation. All right, and then you go on from there, and usually we won't need these higher order terms. It'll suffice to only find out what S0 and S1 are. All right, so the leading order equation, this guy here, 10, is what's called the iconal equation. And its solution is plus or minus integral. Now, the lower limit of the integration is chosen arbitrarily. The upper limit is x, so it's a function of x, square root of qt dt. So notice that what we need to do first is take the square root of both sides and then just integrate that. It's directly integrable. And that's why you get this. Now, why do we get the plus or minus? Well, actually, when we take the square root, we have to take plus or minus the square root. Now, remember, we're assuming here that q is positive, so we're safe in taking a square root. We know we're not going to get any complex, we're not going to get the imaginary unit when we do that square root, so we're safe. Again, A is an arbitrary point of integration. We're usually going to set this to be useful for us for our problem. Oftentimes, A is just going to be 0, sometimes minus infinity, sometimes 1, but always chosen to be useful to us. Now, if q of x is less than 1, then S naught is going to be complex, as we're going to see, but we're not dealing with that case quite yet. The second equation, equation 11, is sometimes called the transport equation in the quantum mechanics literature. But remember, that's just a purely algebraic equation. You just solve for S1. And that works out to be minus 1/4 natural log of q. Remember, q has to be positive to take the natural log of it. And everything's good there because we're bounded well away from 0. And of course, we can bring this minus 1/4 in as a power on q, and this is the same as natural log of 1/4 root of q. And again, this 4th root of q is well defined because q is a positive function. Any questions about that?
S1 prime.
Oh, did I screw this up? Let's see. Yes. It's not a purely algebraic equation, is it? That's good because as I was thinking in my head, this is not the right solution. Not purely algebraic. So we do have to integrate the result. Okay, good. Do you want to go through that? Anybody see that? Should we go through it? Yeah, let's do it. This one's trivial, right? And this one just requires a little bit of work. So what do we get? So S naught prime, that's the first thing we need. 2 S naught prime. S1 is unknown, and we need the second derivative of S. What do we get when we take one derivative of S naught? We have to keep the plus or minus. We just get Q of X, right? Because only the upper limit depends on X. All right, so then we have S1 prime of x. What happens when we take that second derivative of this? Well, we have plus minus, okay, plus minus again, because we're working with this guy, which has a inherent plus minus. So now we need the first derivative of the square root of q, right? So that's going to be 1/2 1 over q of x. That's g of x there. Q of x. And then what?
Q prime.
Q prime of x, yeah. So the plus minus cancels, right? So if it's minus, it cancels. If it's plus, it's the same sign in either case. So we don't have an oscillating sign there. Divide both sides by q. Oh, I forgot my 2 out in front, didn't I? So I have S1 prime equals to 1/4 with a minus q prime fourth root of q, correct?
No, because you
Let's see. Oh, no. Yeah.
divide, so it becomes 1. In Q.
You're right. Now, so now S1 should be equal to, well, of course, we see that this is just the derivative of the natural log of q, this term here, and that's where the minus 1/4 comes from, okay? Where does the constant of integration go, though?
Oh,
Well, so why is there no constant of integration here? Or why do we not have to worry about a constant of integration there? Well, that could produce a constant, but we could absorb that constant in the constant we're going to throw out front anyway. Okay, so that's where that's going to go. Okay, well, actually, this one does have a constant of integration, so we did keep that one, but we can get rid of this one. So the leading order asymptotic expansion, we have 2 branches that we have to take into consideration here. One goes with the plus, and one goes with the minus sign. So the one that goes with the plus is here. And see, I ultimately do have a constant out front. And the one that goes with the minus term is this one here. Now, remember the first order term, what does that look like? Well, remember, it's going to be epsilon times S1, but I'm dividing the whole thing by an epsilon. So that's an order 1. So this constant, if we were to leave it here, is an order 1 constant, and it can get absorbed by this order 1 constant. Where does this guy come from? This comes from taking the exponential of the log of this term. Okay, so does everyone see the structure where everything's coming from? So what we're saying is that basically another way of writing this, or what we expect, is to say y of x equals all of that stuff down below So I should say it like this. All that stuff plus big O of epsilon. That's what's expected as epsilon goes to infinity. If I drop this, then I'm just going to write this with a asymptotic symbol. So that's what I've done. Just drop that. But it's expected that this is the difference between what you see here and what is the true solution is just going to be order epsilon. That's what's hoped and expected. Now we have two independent solutions. But that's not a problem because we have, we're going to have or expect to have two boundary conditions or two initial conditions or some mixture of two conditions that we have to use to determine these guys. So these are currently undetermined, but we're going to use our boundary and or initial conditions to determine them. Does that make sense to everyone? So two free parameters, and they came from the fact that we had a plus minus here. Interestingly, we don't get any solution ambiguity here. And there's the first order or the leading order asymptotic approximation.
This is order one.
Yeah, this is the leading order or order one, what is expected to be the order one contribution. So what's missing would be order epsilon if it really is can be expanded as a standard power series in terms of epsilon. Now you can get higher order terms. So in Bender and Orszag, you can find S2, S3, S4, and S5. So here's S3 or S2 and S3 in case you're interested to know them. So the even number terms come with this plus minus ambiguity, and the odd order terms, you lose that ambiguity for kind of the same reason we lost it here. When we determined this equation, you get plus minus cancellation all the way down. So that's S2 and S3 in case you're interested. So we can do higher order matching. So we could construct a solution or higher order expansions. So we could construct a solution which has expansions up to order, or it's correct up to order epsilon squared. Let's do Q negative next. So for Q negative, our equations are leading order and the first order correction equations look like this and like that. We're assuming that Q is strictly less than a negative number, Q naught. When we do this term, well, in our first order, our leading order term, we're going to write, instead of writing this as just Q, we're going to write it as minus absolute value of Q. So we are definite about the sign of things that go under square roots. So take the square root of this, that automatically gives you the complex unit when you do that, plus or minus complex unit. But then what remains is just something which is positive and can be, or the square root of this thing, which can be just integrated. So that's the leading order S term. The first order equation is similar to that, except that I screwed this up again. That should be prime there. Typo there. Which is good because it doesn't work out otherwise. But it works out in exactly the same way as it worked out before. The plus minus I that you get in front of every term cancels. So that's good. And when you solve this equation, integrating once, again, we don't care about the constant of integration that we would get because that can be absorbed in an unknown constant. And so,
There's a typo as well.
okay.
The first higher order equation is you have a prime.
Which equation?
No, the first higher order equation is you have a
Oh,
forward.
yeah. Maybe that's where my prime went. I'm gonna say that. Yeah, move to here. Like you can do that, right?
It's like 1 centimeter from the correct direction.
Yeah, I agree. But then how did it escape the previous? I don't know. So we do that. No. How do you, oh, okay.
Nobody ever copied.
Oh, okay. It doesn't matter. It's not going to make it right. Okay. So here's our leading order asymptotic approximation. In this case, we can go about expanding it in a similar sort of way, but we're going to recognize right away that we have a exponential, complex trigonometric exponential, right? Of one with a plus and one with a minus. And as usual, these are going to fold into cosine and sine, giving us new constants out front, not necessarily the same as before. What happened there? That's a weird looking one. That's awfully weird looking. Looks like it's shrunk in some way. I don't know. What's that?
Change it to that, you have cosine plus I sine and then cosine minus I sine.
Correct. I mean, it's the standard. It's the same reason why it works out to be cosine and sine in the usual setting. I'm not saying that these coefficients are the same as the coefficients above. Right? It's
But where's the I?
Included in the.
Yeah, so it could, you're just assume you don't care that this is
Complex.
yeah. Generally, and then you argue that it has to be real to begin with. Okay, so like I said, I'm not doing the same rigorous analysis we did for boundary layer problems. I have done a lot of research on this, and it appears that it's just a lot more complicated, which is that makes sense. On the other hand, because I haven't used this as much, it may be my own, it may only be my outsider's view that it's more complicated than the rigorous analysis that's done for the matched asymptotic methods for boundary layer problems. So that should be. Okay, so instead of doing rigorous analysis, let's just do a bunch of examples to see that this turns out to be the right approach. I think that that's how this method was born in the first place. Now there's, physicists have physicists' insights. So I think they were on the track of saying, well, basically this equation looks a lot like, I'm quite sure that it started out like this, that they were saying, well, our initial equation looks like this. What was it, plus or minus? I forget. Doesn't matter. So the equation starts out looking like this, but they argue as epsilon gets smaller and smaller, I can think of in some regimes, this can be replaced essentially by a constant. And so that's where the building of these solutions came from. It looks a lot like that. This, of course, is a sine and cosine or an exponential increase-decrease situation. But there's a little bit more to it than just that, I should say. So instead of analyzing why this is a good asymptotic approximation rigorously, and that you can do this rigorously, and it does work out, let's just do a bunch of examples that show everything looks good. So let's examine the case where Q is equal to 1 plus x squared quantity squared. So this is the case where Q is positive on the domain of interest. The domain of interest is this one. All right, so this one definitely is not decaying down to 0, so we don't have to worry about that happening. Its smallest value is going to be, looks like 1. So our WKB analysis should work. If we plug this Q into our equations, well, it's nice. It nicely works out so that we can do the square roots that we need to do. And so let's first of all, let's look at what do we have for initial conditions. These will determine the coefficients that we have. So our initial conditions, we're going to use y of 0 equals 0 and y prime of 0 equals 1. Then the WKB method produces the following approximation. The reason it produces such a simple approximation is because this can be integrated exactly. The square root can be integrated exactly. And you get that exponential that you get in this case can be viewed as a sinh, okay? Because we have plus and minus exponentials. It simplifies down to just the sinh. And so this is our WKB expansion in this case. And so what I want to do in this case is not go through the tedious derivation of this. I claim it's fairly simple because this can be integrated. The square root of that can be integrated. What I do want to do is show some calculations that give at least numerical evidence that this is quite a good approximation. So let's have a look at the figure on the next few slides. So the first thing you should notice about the solution to these equations is they're definitely not boundary layer phenomena in the usual sense. So in this case, it just looks like as epsilon gets smaller, so this is the smaller epsilon case, epsilon equals 0.01. You know, it's not like these things are converging to the same shape in the same sense that boundary layer phenomena were. This is epsilon equals 0.1, epsilon equals 0.2. The WKB is in blue, and it's right underneath this orange curve. So and this is with not very small values of epsilon, at least I consider, and the WKB method is hugging it pretty tightly. This one is the larger case, and the green curve fits right underneath this red curve, and you could, you know, by the eyeball norm, they're more or less the same. They both, you know, everything satisfies the same initial conditions. Now, the numerical solution that I got for this, I just used Mathematica's numerical ND solve. And so that's what I got. Now, this is blowing up quite rapidly. Bender and Orszag had the same example, and they plotted theirs out to much larger values. But this thing just, if I take epsilon smaller, basically it shoots up earlier and goes up pretty fast. So basically this is growing pretty rapidly exponentially, as you can see from here, right? Sinh gets large pretty fast, but then you also you also have an x cubed here, which is getting large. So this is getting large, this is getting large to the cube. This guy is getting smaller, but it's kind of like linear in x, right? Dividing by x for x large. That can't control this, which is exponentially growing. So it just blows up. So it's not good to look at the comparison of the solutions in this way. What you want to do is look at the relative error. So take the difference and divide by the true solution, and that gives you the relative error. And so with that one, I could plot more values of epsilon without just having them just blow up straight away. So here's the smallest value of epsilon, and you can see that the relative error, you know, both of them are blowing up, so we can't say that it's really converging as they both blow up. But if you look at the relative error, it's getting smaller and smaller as epsilon gets smaller and smaller, which is as we would expect. Okay, so, and I'm pretty confident that I could do the same calculation for half the size of epsilon, and we would see a curve which looks like that.
Why the relative error decay after some decades?
Oh, I don't know, to be quite honest, why it seems to have a maximum here. And in fact, I'm not claiming that it does. It only seems to have a maximum at something which is order 1, but that might.
If the true solution is like going to infinity and your relative error, like the difference term is like not approaching exponential, then you will have this happen.
You know, remember when we did Stirling approximation at the very beginning of the course? And we looked at the difference between the true and the computed solution, and we said, it doesn't look like they're actually converging to each other. These things are getting very large, and the difference is getting large as well. But the relative error can still get small. So this is the sense in which asymptotic approximations can be useful. So even if you have a series which is diverging, if you do a relative error comparison, things can be quite good. Now, so in the last chapter, we looked at boundary value problems that were singularly perturbed, hard to say. We looked at both the linear case and nonlinear case, and I told you, of course, we went through all the theory for the linear case, which was doable. The nonlinear theory you can do, but it's only in a very much a case-by-case basis. So some of it you can do and some of it you can't do. When we do nonlinear singularly perturbed boundary value problems, it's quite nice when we can use the phase portrait analysis to help us. In fact, I found, and one of you asked me about this, how do you solve the last problem on the homework? The nonlinear boundary value problem. Well, first of all, amazingly enough, it has an exact solution which you can find, and you can kind of analyze that solution in terms of what parts should go with the boundary layer and what parts should go with the outer solution, etc. But you can use the phase plane analysis, phase portrait analysis to understand the solutions of that. So if I do know from talking to one of you that doing a dominant balance, first of all, that's kind of one of the easiest things that you can do and seem to work in most all cases. Turns out the dominant balance fails to determine what the right delta parameter should be for your boundary layer thickness. But some other things work, like, for example, if you know how to compute the true solution, you can immediately see that delta should be of order epsilon. And then the other thing you can use to your advantage is use the phase portrait analysis. That helps you determine how the solution looks. So a couple of hints there, I guess. Now, at least we had some theory that we could use sometimes. The WKB analysis is not going to work usually for nonlinear equations. That's because you're proposing a lot of structure with the solution from the beginning. You're assuming that this solution is exponential plus some sort of expansion, and that doesn't work for nonlinear. But we're going to see that actually you can use it to study these linear singularly perturbed problems. For example, our model problem was this one. Y or epsilon y double prime p of x y prime of x q of x y of x equals 0. Epsilon between 0 and 1, but of course epsilon should be a small parameter, and then generic boundary conditions. So let's assume, as we did before, that p of x is greater than 0 for all x in 0, 1. I forgot to say here that p of x should be a continuous function, but that's maybe understood. So according to our theory, for every epsilon small enough, there's a unique solution to our problem. So we showed that with theory. We also said that there was a boundary layer of thickness delta equals epsilon at x naught, x equals 0. And the composite uniformly valid approximation that we got by doing matched asymptotic expansions was you take your leading order outer solution plus the leading order inner solution, and you subtract off the matching term. And here's our outer solution. It's some exponential involving an integral of the quotient p over q over p. And the structure of our inner solution, remember we said an inner solution in the linear case has to be characterized by this exponential decay. And that's actually what we use to locate where the inner where the boundary layer was. So the inner solution has this form, and the match term has, or the overlapping term is just this. It's just a constant. If you put all that together, then our composite approximation looks like this. So you're probably saying, who cares? We already have done this. What's the big deal? Well, the interesting thing is that WKB method can reproduce this result, and it can do it in such a way is that it puts it together in a global fashion, and you don't need to do any kind of matching between an outer solution and an inner solution. You don't even have to worry about where the boundary layer is. It knows somehow. Now, it doesn't matter whether P is positive or negative. If P is negative, then it will understand to locate the bound. It's a little bit like AI, you know, it's the original AI. So it'll know that the boundary layer is at the right-hand endpoint rather than the left-hand endpoint. Seems kind of magical, but that's because WKB is a global method, and it kind of takes care of everything at once. Now, to begin with, we're going to insert our approximation or solution ansatz into the equation. And then we try to determine delta from dominant balance. Now, the first thing we do, of course, is because we're assuming everything, the solution has an exponential form, that exponential term appears in every term, again, because of linearity, and I'm going to use cancellation property to get rid of that. Now, we know that the complex trigonometrics can be equal to 0, but that's, you know, they're only 0 at, you know, for certain numbers. If it's the dissipative case, then of course the exponential is real and it's never equal to 0. So you're safe. You can use it, the cancellation property. Either way, cancellation will work in both cases. There are 4 terms in this equation. It doesn't look like I can reduce this to less than that. So we'll take that at face value. There are 4 terms. And let's try to do dominant balance in the usual sort of way. It turns out in this case, there are 2 different dominant balance scenarios that are possible, which is kind of weird because when we did this using our other methods, there was only 1 dominant balance possible. So first of all, the 3rd and the 4th terms above may balance. If that happens, and this is order 1, then we find that 1 over delta is equal to 1. In other words, we get delta equals 1. So what do we do in this case? In this case, terms, as I said, terms in 3 and 4 order 1, provided that Q has no zeros. And terms 1 and 2 are thus of order epsilon, which is dominated by order 1 terms. So that balance works out. However, this balance only gives us the outer solution. All right. It only gives us the outer solution, and it only gives us the outer solution by itself. So for this reason, we have to reject it. So you can work through the details, but you see you don't get the full solution in this case. But that's okay. The outer solution is at least something. The other possible dominant balance is from equating the coefficients of terms 1 and 3. So term 1 is here and 3 is here. So in that case, you get epsilon over delta squared is equal to 1 over delta. And so you get delta equals epsilon. That's what we want and expect. And this suggests that terms, or the coefficients of terms 1 and 3 are of order epsilon to the minus 1. And terms 2 and 4 are of order 1. So this dominant balance is viable. And so that's the one we're going to use. Okay. This one actually leads to the full global asymptotic picture, which is more useful, obviously, than the previous case, which only gave us the outer solution. So if you plug in this knowledge that delta is equal to epsilon, then this is the equation that we get. Okay. Now, technically speaking, I should probably write this with tilde, because we start off with a solution assumption that well, I can't go all the way back, but the assumption begins with assuming that y is simply and S is a power series expansion usual in integral powers of delta. So technically I should write it like that. But as I said, we're not being as careful mathematicians here. We're being more physicists than mathematicians in this chapter. So now we're going to insert the expansions for S and its first and second derivatives into our last equation. And then we repeat the process of determining the equations for all possible orders. So for order 1, we get this equation, assuming that I haven't made any mistakes in that. And for order epsilon, we get an equation which looks like this. As before, we don't determine in this approach, our order 1 equation is not a second order differential equation, but only a first order one. Okay, the order 1 equation has the leading order or order 1 equation has 2 possible solutions because you can see that there's an S naught prime in both terms. We can factor that out. So either S naught prime is equal to 0 or S naught prime is equal to minus P of X. It turns out we have to use both of those. So that's going to give us our 2 linearly independent solutions. This works out in exactly the same way that in the O'Connell equation, we got a plus or minus. So we have to take consideration of both the plus and the minus to get 2 linearly independent equations. So let's suppose first that S naught prime is equal to 0. So that means that S naught is a constant, and the order 1 equation simplifies to just this. So that's a first order equation that is integrable. We can divide by P because we know that P is not 0. And we can just integrate that to give us this. Now we're going to use the lower limit of integration as 0 because why not, right? That'll turn out to be useful for us. So that produces this approximation. And if you're eagle-eyed, you can see right away that that's just the outer solution, the outer approximation. So that C1 is going to be a constant that has to be determined. Let's try to find a linearly independent second solution. Well, that's going to be obtained by using this other branch of that nonlinearity. So this order 1 equation then becomes, and so we don't have to worry about what this guy is, do we? So this guy is just the antiderivative of minus P of X. But really what we need is to figure out what is S1, turns out. In the order, let's see. This should say the order epsilon equation, shouldn't it? Is that right? No, let me check. Yeah, it has to be the order 1.
Because you substitute S naught equals 0 to the second equation, you get the equation you get on the next slide.
I think I made the same mistake here. Right? So this one has no S1 in it, right? Once we determine S naught, we plug it into this equation. Here, those go away. We can collect terms of S1 prime, okay? So that should be order epsilon equation simplifies to that, which is integrable. And then this is the order epsilon equation for the second case, second branch. I just was confusing myself because I had a typo. So I claim that this one has the solution minus log p of x. P of x is positive, so we're safe in computing that log, plus the integral from 0 to x of q of t, p of t, over p of t. All right, so you can check this since time is a little bit short. I'm just going to assume that this is true. Let's see, is it pretty clear though that this is the case? Yeah, so why is this true? Maybe you see it right away. Well, this is, we know what the homogeneous solution to this is already, right? And then we can construct it by a homogeneous plus particular solution, right? So if we do the homogeneous plus particular solution, then you'll see it right away. So what is the homogeneous solution? Well, we throw this to the other side, we divide by p, and that's going to be the minus the log term. And what about for our particular solution? This has to be the particular solution in this case. Looks like a fairly complicated particular solution. Not sure how you would arrive at that right away. Does anyone see why?
Just plug in.
Yeah, just on the first,
Well, yeah, you can plug it in, of course, and see that it's right, but
I mean, if you really say like,
yeah,
just do the regular integrating factor.
yeah, I mean, integration factor works, yeah, for sure. It's not a form that I would just naturally guess, let's say. But yeah, it's not too bad. Oh, actually, no, it's even simpler than that, isn't it? It's even simpler than that. Right, because this is just a first order ODE. It's purely integrable, right? So we just divide by p of x and we get a natural log term there and divide by p of x. You just integrate both terms. It's linear. Just integrate both of them and you get these three terms. So I guess we did have time to check it because we did. So this solution branch produces the following. Check it. So it should be C2 over P of X. The P comes because we're exponentiating this log term. So we get that P popping out. An exponential of all the rest that's left. Where C is an arbitrary constant. So this I'm claiming is going to be all the rest of the terms in the composite solution. So not just the inner solution, but the inner solution minus the constant C1.
So we already get rid of the double count from.
Yeah, so this one takes care of double counting right away. All right, so this one is the outer solution term. So this one has to be, if it's correct, at least asymptotic to the inner solution plus or minus, I should say, the constant of integration, or not the matching term. So what the target that we're shooting for is that the solution should come out to be like this. So we already have this piece isolated. Well, we have it partially isolated, I should say. We don't have the constants determined yet. We should do that. I won't be able to finish this in all details, but we'll come back to that. All right, so let's impose the boundary conditions that we have at x equals 0, y should be equal to a. At x equals 1, y should be equal to b. And I claim that doing that gives you two boundary conditions. If I plug in x equals 0, then you can see right away that this just becomes 0. So this is e to the 0, which is just 1. So that's why you only get the C1 term. If I plug in x equal to 0, these also go to 0. And so I just get the C2 over P of 0 for that. So that's clear. What about this guy here? When I plug in x equals to 1, then I get a bunch of terms which are exponential with this term here. Let's see which ones. So this guy and that guy are the same. Except that one has a sign difference, does it not? This one has a minus sign, this one has a plus sign. But what about this term here? When I send this to 1, then this becomes just some integral order 1. And it's accompanied with a 1 over e term. So this is exponential to something which is getting minus positive infinity. So this is becoming the transcendentally small term. And I claim somehow that what's left are these two pieces. But I'm not seeing it exactly. Where did this term? Oh, I see it now. The reason is because I can just say, you know, this is just some integral, so it's a constant order 1. But this is dominating as epsilon gets large, right? Because it's becoming negative infinity. So something positive order 1 plus negative infinity, when I take the exponential of that, the whole thing is transcendentally small. So all that's recovered is just this term. So then allows us to solve for C1 and C2, I think. No.
Yeah.
No,
Where-
I'm missing a C2. Oh, no, here's C2. Sorry. Okay, so this does allow us to solve for C1 and C2, and I claim that what you get after dropping transcendentally small terms is this. So this is where we'll pick up next time. Okay, I've got a couple more terms which we need to cancel in order to get to our final result. But the idea is that the WKB method can obtain that method that we have, or obtain the solution that we got by matching, but doesn't do matching at all. It just does this from a completely global perspective. All right. Thanks for giving me an extra 2 minutes. I might give them back someday, might not. But if you have any questions, come up afterwards or send me an email. Otherwise, I'll see you guys on Thursday.